Bismillahirrahmanirrahim. Dear students, let's start from the point where we left in the last lecture. We are here with the B part of your lecture number 7. We were discussing a scenario where how do we add 32-bit words on a 16-bit hardware. So we had discussed that what steps to be taken. Briefly, I am again recalling it for you that adding two 32-bit means that we divide our 32-bit word into two 16-bit words. One would be the 16 bits would be least significant, and the lower order bits, and the remaining 16 bits will be the higher order bits. So these lower orders and higher orders will make a full 32-bit word, and we will add it one by one. Means we will first we will add 16 lower order bits, and then we will add 16 high order bits, and moving the result from the internal registers to the disk. So moving forward, microcode variations, restricted or full scope. So microcode variations in this special purpose instructions only. For example, extensions to normal instruction set, and all instructions. It includes microcode variations, all instructions, partial or complete use, entire fetch execute cycle, instruction fetch and decode, opcode processing, operand decode and fetch. So microcode variations can that with the variation in the microcode we can change anything. I mean that with the restricted scope or full scope, we can change all instructions or the partial part of some fetch execute cycle, or the entire fetch execute cycle can be changed, or the instruction fetch and decode mechanism can be changed, or the opcode processing. So anything, whatever we want to change or we want to vary, we can achieve it through the microcode variations. And why use microcode instead of circuits? Because it is a higher level of abstraction and easier to build and less error prone, because the circuits are more complex, and for that engineering considerations need to be taken into account, and a lot of designing and optimization is required. But in contrast to the circuit design, the microcode is a higher level of abstraction. It doesn't need us to move into the circuit designing details or redesign of the circuit, and it is easier to build and less error prone. That is why it is more flexible and easier to change. If you want to change something in the microcode, so we can easily change and easy upgrade to next version of chip. This you might have seen that the IPTV modems provided by the PTCL or the DSL modems, or where yes, let me recall some other examples as well, that you can your Android mobile phones. All of these can be upgraded to the higher firmware, higher degree, higher order firmware whenever the new version comes. So automatically these devices, they check if they are connected with the network, so they check their availability of the new version, and it asks you that whether you want it to auto update, or and if you make it yes, so it download it and it automatically upgrades the firmware. This is the same thing, that easy upgrade to next version of chip, and it can allow field upgrade. Field upgrade means that no need to bring it into the lab and dismantle it from the chip on which it is there. Instead of it, there are the mechanical switches on the chips, which are called field programmable, and by using the combination of on or off values of those switches, we can reprogram these chips. So this is another advantage of the microcode. And the now comes towards the disadvantages of the microcode. So it is more overhead, because it is not conventional method, and not easy to grasp all the details. So it is more overhead. Macro instruction performance depends on micro instruction set, and the micro instructions depends upon the hardware. So the macro instruction performance depends on the micro instruction set. Uh, Microcontroller hardware, uh, must run at extremely high clock rate to accommodate multiple micro instructions per macro instructions. So because the macros are deployed with the help of microcode and micro instructions. So microcontroller hardware must run at extremely high clock rate to accommodate multiple micro instructions per macro instruction. So higher power is required on the processor side. So this is the disadvantage of the microcode. And another one is the visibility to programmers. Fixed microcode and the alterable microcode. There are two types of microcode. One is the fixed microcode, and the other one is alterable microcode. So in the fixed microcode approach used by most CPUs, the fixed microcode approach is used by the most CPUs, and the microcode only visible to CPU designer. Means the users cannot, because as they cannot change anything, so it is not visible to them, and only the CPU designer that can see it. And fixed microcode approach, it does come with normally mostly all the CPUs. But on the other hand, the alterable microcode, this microcode is loaded dynamically and may be restricted to extensions, creating new macro instructions, and the user software written to use new instructions, and known as reconfigurable CPU. So the alterable microcode is also called reconfigurable CPU, because it is visible to the users, and it is possible to create new macro instructions, and the user software written to use new instructions. So reconfigurable CPU. What is reconfigurable CPU? Some CPUs provide a mechanism that allows microcode to be rewritten. The motivation for allowing such change arises from the desire for flexibility and optimization. The CPU's owner can create a macro instruction set that is optimized for a specific task. For example, if I tell you that we are dealing with the network devices, switches, routers, access points, and firewalls, etc., so their role is restricted. Means they need to analyze the traffic, they need to forward the traffic, and in all this cycle, they need to examine the headers, and then read the operating system commands, and that what to do, and the configuration file, that what to do. So their role is very specific. For example, the case which I'm telling you, these devices will never work as a camera or as a scanner or as a printer or any other designing tool. So their role is very specific. So in that case, the a reconfigurable CPU is the very good choice, because the mechanisms that allows microcode to be rewritten, that for the optimization means that fine tuning. The fine tuning is also called the optimization, and we can optimize, we can get the more out of a box by reconfiguring or by rewriting the code. So this is the plus point of a microcode, that or the CPUs, that they are reconfigurable, that the same device, for example, for the same device we can use it as a server, and the same machine can also be used as a client, and similarly the same machine can be used as a web server, and in the other times, if I change my mind and if the requirement does change, so we can reconfigure the same hardware as a web server client. So this is the flexibility which we achieve through the reconfigurable CPU through microcode. And in practice, writing microcode is tedious and time consuming. That as I told you, that this is not very straightforward, that it's not liking taking dictation in the English or like that. So writing microcode is tedious and time consuming, and its results are difficult to test. So there will be the possibility of an error, and it will be time consuming process to fix it. Performance of microcode can be much worse than performance of dedicated hardware. This is a negative point, that the performance of microcode can be much worse than the performance of the dedicated hardware. So because whenever something is used in the sharing mode, so there is the desire to overcome and to use the hardware simultaneously for the different purposes. So in that case, the shared devices, they cannot give the optimum performance for the both uses, shareable uses at the same time. So this is a very big bottleneck which comes in the processing of the servers and in the network. For example, if I share a link between 3 users, and I guarantee them that they can jump up to 50% of the maximum allowable limit of the link. But in normal cases, they will be getting the at least the 33% of the maximum allowable limit of that link. Now consider such a time in which all of these 3 customers have the high traffic rate. So everybody will be starving for the bandwidth, and nobody will be getting the 50%, which I committed them that whenever it will be available. So they can get up to 33%, but nobody will be getting the 50%, because the media is shared, and we have committed our clients that we will ensure the 33% bandwidth availability. So this type of service is called bus stable service, and with the CBR of that committed bit rate. CBR means the committed bit rate of the 33%, and then it is bus stable up to the level which the service provider tells the client. So the performance of microcode can be much worse than the performance of dedicated systems. So it's obvious that whenever something is available dedicatedly for a piece of software, so it will run very smoothly, and its performance will be much higher. And the result of all the discussion is this, that the reconfigurable CPU have not enjoyed much success. So because it's tedious and not straightforward, and shareable hardware, the performance of the microcode can much worse than performance of the dedicated hardware. So the reconfigurable CPUs have not enjoyed much success. And two fundamental types of microcode. What programming paradigm is used for microcode? So two fundamental types of microcodes. One is called vertical microcode and the other is called the horizontal microcode. Let's discuss them one by one. The vertical microcode, this is the conventional microcode and microcontroller similar to standard processor. Microcontroller, several times we have discussed this, that this is altogether a full computer, but it doesn't have the mouse and keyboard and the VDU display. So instead of it, it has a small keypad like calculator buttons, and we use it for the input signals, and like calculator has a small output screen, so it has also the almost similar screen for the output to display. So, and the vertical microcode similar to the conventional assembly language. Like the assembly language, it is written from left to right and top to bottom. So the vertical microcode is also similar to the conventional assembly language. So it is also written in the top left to right and top to bottom. That is why we are saying that it is similar to the assembly language. And it typically performs one operation at a time, has access to all facilities macro instruction set uses, ALU, general purpose registers, memory, IO buses. So it can access, or it can have the service from any parts of the CPU. So example of the vertical microcode is macro instruction set in CISC, and the microcontroller is fast RISC processor, and programmer writes microcode for each macro instruction, and hardware decodes macro instruction and invokes correct microcode routine. So these are the examples of the vertical microcode. But I tell you that the vertical microcode is the conventional microcode and easy to read. Programmers are comfortable with using it, unattractive to hardware designers because higher clock rates needed. So this is the drawback of the vertical microcode, that it is unattractive to the hardware designers because higher clock rates are needed to achieve a better performance. The underlying hardware will need to be upgraded, or the higher clock rates would be required. So clock needs to be upgraded, and generally has low performance. Many micro instructions needed for each macro instruction, as we saw in the previous example, that when we tried to add two 32-bit words in at a 16-bit hardware. So you saw that we completed this step in almost 7 or 8 steps. On the other hand, if we could have a similar kind of hardware, that is 32-bit hardware, to add two 32-bit systems, so it might take not more than three steps. So this is the complexity which we have, and the systems becomes extremely slow because it needs to that we are avoiding the hardware upgrade and we are trying to fix it with the vertical microcode through the software. So very the most the 3 or 4 times more instructions will need to be written, and there would be many iterations in the softwares to carry out some execution and computing the results. That is why it is unattractive to hardware designers, because higher clock rates are needed. Generally has low performance, many macro instructions need for each macro instruction. This we have seen in the 32-bit word addition, and the other on the other hand, the second option available, it is horizontal microcode. So horizontal microcode is alternative to vertical microcode. Both of these do the same work. For example, if I go to from point A to point B on a Alto car, and I can go from the same point A to point B on a Corolla car. So this is the likewise they are both of them are similar for the same purpose, but they are the different mechanism. This is alternative to vertical microcode and exploits parallelism in underlying hardware. So as the hardware is being upgraded in all the coming versions of computer manufacturers, so it exploits the parallelism in underlying hardware. So obviously it makes the fast processing and which is and doesn't require the more clock cycles contrary to the its old competitor, the vertical microcode. This is more attractive to the programmers, and it controls functional units and data movement. This is another plus point of the horizontal microcode, that it can control functional units and the data movements as well, and it is extremely difficult to program. This is the drawback of the horizontal microcode, because it is unconventional and new mechanism, and it is extremely difficult to program. But the plus points are that it exploits the parallelism in underlying hardware, and it control functional units and data movement as well. So we will be discussing a little bit more things about horizontal microcode. The important trade-off with horizontal microcode. Horizontal microcode allows the hardware to run faster, but is more difficult to program. So this is unconventional. That is why, because I tell you that in the starting days of the computers, people used to be afraid of computers. In fact, whenever somebody was deployed on a computer-based job, people started using their political pressures and their influences to get the transfer from that post. So to overcome this situation, the governments they announced the computer allowance for such jobs which involve the use of computer. But this, I'm telling you, almost 30 years ago, 25 to 30 years ago. Now the landscape has been completely changed. Now everybody is comfortable with the computers, with laptops, and mobile has changed all the landscape. So now the shyness or the hesitation to use the computer, that is over. So similarly, in this case, the horizontal microcode allows the hardware to run faster, but it is more difficult to program. Because whenever some new syntax comes or the new language comes, it requires more effort by the programmers to grip on it. So this is the same case, that horizontal microcode, the vertical microcode was similar to the assembly language, that assembly language is written from left to right and top to bottom. So vertical microcode also used to be written in the same way. But the horizontal microcode, horizontal, like its name is telling us, it's not that much simple. So that is why it is more difficult to program. And in this paradigm, each instruction controls a set of hardware units, and the instruction specifies transfer of data, which hardware units operate. So we will be discussing this through a model coming in the next slide. So these are the this is the outline or the sketch of the horizontal microcode, that each instruction controls a set of hardware units, not only a one hardware unit, rather it controls a set of hardware units. Means whatever we discussed in 2-3 slides in the previous slides, that it exploits the use of parallelism. So that is coming here, that each instruction controls a set of hardware units, and the instruction specifies transfer of data and which hardware units operate. So how does this happen? We will discuss it with the help of a model. So a horizontal microcode example. This is the model which you are watching at your screens right now. That it's consider the internal structure of a CPU. That a CPU has arithmetic and logic unit. It has the operands, operand 1 and 2, and the dedicated registers for the result. And dedicated registers for the result. And there is a register access and the macro general purpose registers. This is the model. Consider the internal structure of a CPU, and data can only move along specific paths between functional units, and these specific paths are also called buses. And we have different buses in the computer, right? Like address bus and the data bus and control bus. So different signals travel over them, and the point to note on this model is that all the elements shown on this model, they are connected with the other hardware units through the bidirectional bus. That it means that the data can be moved in either direction, into that element or out of that element. So let's discuss this slide. So we were discussing this figure, that it is bidirectional on the data can move on the either side. So we can see here that the example hardware control commands, that ALU has 3 bits, and the meaning of these 3 bits are different for each combination. That if 000 means no operation, 001 means add operation, 010, if we have this combination in the ALU, it has 010, so it means that it will subtract. If we have the command code of 011, it will multiply, and 100 will divide, 101 will left shift, and 110 will right shift, and 111 will continue previous operation. So these are the possible command set commands available for the ALU. Then comes the operand 1 or 2, and for this 0 means no operation, and 1 means load value from data transfer mechanism, and result 1 or 2. Then comes the registers, the other unit result registers, and 1 and 2, and here again the 0 means no operation, and 1 means send values to data transfer mechanism. And similarly, the register interface, it has a 6-bit value, and the most significant 2-bit 00 means no operation, 01 means move register don't care means 4 access to data transfer mechanism. 10 with 4 don't care conditions, it moves data transfer mechanism to register number XXXX. And 11 means no operation. So thank you very much, students, for listening this lecture, and we will continue in the next slide, that what to do with it, and for this lecture we have completed our specified time. So let's meet in the next class of this lecture. Okay, assalamu alaikum.